Actually, not seats, chairs. Otherwise, you suggest people to just go upstairs and sit there.
Yeah.
So let's start. Okay, so we'll start. Okay, so yeah, first a seminar / lecture by me about 3D data compression. I tried to make it relatively beginner friendly, but if there are any questions, please interrupt me. It's better if this is more of a discussion than just a lecture where everyone's silent. I'll try to use the whiteboard as much as I can because mostly the presentation is like a cheat sheet for me to tell you different stuff. Okay, so there's going to be somewhat of a plan. I should break up the presentation show so like this. So you can see this. Yeah. Okay. And sorry. Okay. I hope I'll be able to use the whiteboard properly. Okay. So there's going to be a plan. I'm going to go through like base concepts before the juicy stuff. I'm going to talk about like the introduction to what I mean by 3D. That's 3D meshes, various representations that come from 3D reconstruction. There's of course 3D in immersive VR video, which is like an upcoming field right now. And I'm going to go through like the basics of video compression, the basics of like basic file video. File string compression that is widespread and used everywhere. And then after the prerequisites, I'll go through the concepts that I want to discuss. The mesh/animation compression in game development. There's one example that I want to show. Some research in mesh compression, the compression of Gaussian Splatting, which is an upcoming topic in 3D construction, and compression of dynamic NeRFs. These two concepts are something I've been talking a lot about on Paper Reading Club. You may not be familiar with it, but I'll try to introduce you if you're not. Yep.
I think it's possible to close the format options panel on the right.
Ooh, that's right.
Gain some more space on the screen.
Yeah.
Wow.
Good.
Nice.
Also, I'll try this. Nope. That's not great. So, let's go. So yeah, I have like a main motivation behind this particular talk. First, I wanted to discuss one particular paper that really I thought was great, which is called Video RF. It's basically NeRF, but video. I'll explain what NeRF is later. But this is the result. I'll just show you quickly. Ooh, can I have some audio? Ooh. Yeah, sorry. 1 second. This should be right.
Headphones. You should use headphones.
Headphones.
We present Video RF, the first approach to enable real-time streaming and rendering of dynamic radiance fields on mobile platforms. We develop a real-time player to allow users freely render appearance and geometry. Users can rotate, drag, zoom in, zoom out, fast forward, backward, just like watching online videos. We can also offer this immersive experience across a wide range of devices, from laptops and desktops to smartphones and tablets. Our method can...
Okay, so the main idea that I want you to take off is that this looks like a video, but it's actually a 3D video, so it's actually a 3D human that you can rotate around on the device. And the wonderful thing behind this is that it's based on a method called NeRF. And the original NeRF paper barely renders 1 frame in 30 seconds, and this runs in like 20 to 30 FPS on device. And this at 30 seconds on an NVIDIA V100, so it's a super powerful GPU, and it barely renders like a frame in 30 seconds. This renders 30 FPS on a mobile device, probably like pretty new model device, but still, this is very impressive.
So this initial V100 result, is it due to bottleneck on compute or I/O? Like, is it because we need to load stuff in and out of the GPU, or is it because compute is hard?
So it's because of compute. So right now I'm not talking about I/O. So there's two parts about this. First, we can render this very efficiently in 30 FPS. Second, these videos are not actually stored on the device. They're stored somewhere in the cloud. And then while the video is playing, it's loaded up, which is surprising again because I'm not saying this here on the slide, but NeRFs and more so video NeRFs are very heavy. They're hundreds of megabytes or gigabytes of memory to store that model. So this is very impressive. I'll show why it's so impressive later. This was the initial paper that I wanted to discuss, but then I realized it's not just NeRFs that suddenly need or use lots of ideas for 3D compression. There's of course game development where they have lots of 3D assets and they somehow need to store all that in the video game binary files or stream that in runtime. Also there's Gaussian Splatting, which is another thing that stands for NeRF, but it's different and it's better in many ways. And there's some research on 3D compression that I looked at that is also pretty interesting. So yeah, like a quick prerequisite. Who knows what a 3D mesh is? All right. So yeah, not everyone knows. I'll introduce this quickly. So a 3D mesh is a way to represent some 3D object. Here is like a cube. You can probably see that it's a cube. If we would draw a cube, it would look something like this, where we have a front square face, these sides, and also like sides in the back. And so a mesh is a way to represent this cube in computer memory. You can see like the file that is usually used to represent a mesh. What it does is this V actually means vertex and this F means face. So each of the vertices of this cube, there are 8 vertices. The coordinates of each of these vertices is stored in the file, and then each surface face is actually split into triangles like this. So like this square face is split into triangles. And each of these triangles is represented by the indices of the vertices. So for example, this face, 1, 2, 3, means that it's a triangle consisting of these 3 vertices, 1, 2, 3. This 4, 7, 5 face means that it consists of the 4th, 7th, and the 5th vertices. So I have a quick, I can quickly show very hands-on how this works. So I have this cube here. This is literally the cube that I was drawing. I can show you that, yeah, this is a software called MeshLab. It's specifically for looking at meshes and working with them in various ways. So this cube is broken up into triangles. That's how it looks. And if you look at it as a text file, here, this is exactly what you see. So yeah, it's whatever. So there's 8 vertices and there are 6 faces. Each is broken up into 2 triangles, so there are 12 triangles there. Okay.
So this one was handcrafted.
I could have copied it from the internet, but ChatGPT helped me like quickly create this because I couldn't find just a simple cube mesh. Usually this.
That screenshot in the presentation is definitely machine generated. You see it by 0.9999.
Yeah.
This looks handcrafted.
Yeah, and also these files usually have some metadata, so all these vertices have like normals or additional tangent vectors or UV coordinates and stuff like that. But that's sorry. I wanted to show like the simplistic example of just a cube.
Normal is calculated automatically because of the ordering of the vertices.
Actually, what's surprising is most of the times normals are stored explicitly, and it's a trade-off. You can either infer them in runtime, but that requires some computation, or you can just load them in runtime and not have to compute them.
I suspect it's mostly, if it's flat thing, yeah, you get the right normal, but if it's not flat, then you can supply the correct normal for better rendering.
So most of the time, you actually, when you work with game dev, you have explicit normal maps, so you don't actually.
But they correspond to like actual or at least smoother surface.
They're very
That's
very
fine.
close to the true normals, but
Yeah.
Okay, so this was also have another mesh. I'll also show it in another example. This is a frog. I'll show how I got this frog later maybe, but we can also look at how this looks as a mesh. So it has colors in different places, but it also like just consists of many triangles. And so basically any like solid 3D object can be represented with triangles covering the object like this. Yeah, back to representation. This is a 3D mesh. This is the most typical way of representing 3D objects. It's used in game development, in almost any 3D software. So yeah. So now on to 3D reconstruction. So why I'm mentioning this? First, it's one of my favorite topics. It's there are many powerful algorithms to reconstruct 3D objects, 3D scenes from photos. So this is an example where this is a paper. Authors scraped like hundreds or thousands of photos from the internet, like a district near the Colosseum, fed it into an algorithm that is 20 years old. It's a pretty old algorithm, and they managed to reconstruct the point cloud of the district with the Colosseum. So it's very powerful, works very well, but it's a point cloud, and this is a 20-year-old algorithm.
Wait. So what do they have as input and what is?
As input, they have just the 2D photos from tourists
Yeah.
that they scraped from the internet.
Yeah, the main problem of the cool map is you really need a lot of photos there to reconstruct some kind of a 3D mesh. If you just have a few of them, yeah, it's generally it's a problem to reconstruct some of the meshes.
And so each of the red points here represents one tourist photo. So this is like, if you can count the red photos on this image, that's how many photos they needed to reconstruct this whole scene, or this whole point cloud of the district. Yeah, this is a link to the software. It's actually not 20 years old, it's from 2015, but it uses algorithms that are pretty old. But that is, again, pretty old software algorithms. There are modern algorithms that work like wonders. So this is, what I said, NeRF, but this is a variation of NeRF called ZipNeRF that is state of the art in terms of the quality of reconstruction, and you can look at the results in the video.
I'm Baron from Google Research, and this is the supplemental video for a ZipNeRF paper. This video only has results, so if you're interested in learning how this works, please check out the paper. Here's a video that was rendered from our model. This is a large scene that we captured ourselves to push the limits of what NeRF algorithms can do and to expose some.
So yeah, this isn't a video that they filmed with a camera. They took a lot of photos of this apartment, fed it into the algorithm, and then they can render with a program all of these images. So this whole video is rendered actually.
One of the problems that existing models have in dealing with challenges is.
And like, what is the order of the number of pictures of flat pictures they have saved that?
Ooh, I actually don't remember. I gotta look at.
They have all the pictures there. This paper, as you remember, check this paper. And the main problem there that you need to have like a position of the camera.
Yeah. So yeah, these algorithms work accurately like this only if you have images and their accurate positions in 3D space and their like 6 degrees of freedom positions. But that can be retrieved with photogrammetry, which are old algorithms, but they work somewhat reliably. You can try to also like fine-tune all of these positions and rotations that you get from the old algorithm, but in the end it's pretty reliable. So you don't need actually to somehow calibrate your camera and then pass all these positions. This can also be done automatically.
But the trade-off is rendered very slowly.
Yeah, so this is a very powerful algorithm for 3D reconstruction, but yeah, this is not on this slide, but it's rendered at about 5 FPS on, again, a V100 GPU, so it's not very real time. And what else do I want to say?
And
Yeah.
point clouds, they easily can be run real time.
You don't really render point clouds. Point clouds are just like 3D information. Like you wouldn't be able to properly make nice renders out of this. But yeah, so Pasha is probably hinting at this, which is a structure that is very similar to point clouds, but can also be used for very powerful 3D reconstruction. So this is also a render.
We show that 3D instructions for the design.
And this can be run like 100 FPS, so very powerful in terms of like speed.
Space.
There's a modern paper named Smurf, and it's like the next step of deep nerf, and there it's like rendered on the laptop. So it's like a topic with the Gaussian Splatting. You could read every day new paper in there. That's why it's updated very fast.
Yeah, so I heard Smurf mention. I actually considered adding it to this presentation, but there was already a lot, so maybe another time.
Just for kind of an intuition about the field, would you say that most advances in NeRFs are currently algorithmic or like computational? As in, is it just engineering stuff, or is it
I'd
new
say
insights?
there's lots of engineering insights. So Smurf, again, is a paper that does very optimal streaming of static scenes, and there's lots of engineering ideas, like new ideas that were either scarcely used before or were introduced in that paper that really help efficient rendering and efficient storing.
Right. So another way to ask my question is the mass done? Like, is the mass absolutely done, and are there only engineering insights to be found? Or
What do you mean by mass?
I mean, like the theory, I guess, as in Gaussian splats, a new like abstract idea, and particular insights about how to show it into CUDA or something are engineering ideas.
Yeah.
And
So I'd say that both Gaussian Splatting and NeRF are in, like the theory behind them is done. So it's pretty easy to write on the whiteboard like what NeRF means. Like it's an implicit function to represent a 3D object. Well, for Gaussians it's like just ellipsoids, semi-transparent, and then there's lots of engineering to how to represent that function in NeRF, how to structure those Gaussian splats in memory, runtime, and stuff like that. Yeah. So these two representations are probably going to be already somewhat widely used for like VR immersive video, or just you can search and find some web viewers of Gaussian splats. And it's very crucial that we have ways to store them efficiently, because I'll later say lots about this, but for one 3D Gaussian splatting scene weighs approximately 1 gigabyte, 2 gigabytes, and that's not something we can stream for one scene.
And one scene is like one room in a game.
Yeah, so for example, this particular scene, it's probably like from 1 to 2 gigabytes to look at this on your PC. But there are ways to get it down to 100 megabytes or even 20 megabytes, where there is a hard trade-off between quality and storage space, but this can be done. Okay, so next slide.
Do NeRFs work only with NVIDIA?
Sorry?
Do NeRFs work only with NVIDIA chips or other ways?
This is just an engineering question. So any neural network can, like, depending on the framework, can either be trained on NVIDIA chips or AMD chips or whatever, like on TPU. Yeah, so you can get into Google Colab, and like Colabs and NeRF will work on TPUs too, for example. So it's like it's not depending on the neural network or the architecture. It's depending on the framework. So for example, PyTorch should work with AMD chips or whatever. So yeah, and about immersive VR video, there are lots of examples like this. I want to show this. I actually have a VR headset, and I tried this particular app that does VR immersive video. You can basically, like, inside of the headset, look at these 3D videos.
They have Dream View, yes?
I'm actually not sure. I didn't look at what.
The technology is different.
I'm not sure, honestly. Maybe you're more familiar with this. So what I want to show is well, maybe because of the internet. But basically, this is like a short movie, like 5 minutes, and it's all in 3D. You can navigate, like, rotate your head and look around the characters. Whereas if you look at panoramic video, which was often like the 3D video from YouTube, it's basically 2D video projected on a sphere, and you can look around, but there's no like panoramic effect. You can't actually look at the back of an object.
It's not panoramic effect, it's parallax. Now with NeRFs and Gaussian splatting.
Oh, parallax, yeah, sorry, I mean parallax. Okay, it barely shows, but point is, this is a 3D video. You can actually look around, parallax, stuff like that. Okay, so this was cool. I try to see how this works. There's also stuff like this. It works not as well, but apparently works on a phone or in VR. So yeah, they can look at this from a phone, from a VR headset. So this is a sneak peek into how maybe Apple's spatial video will look. So the Apple's headset, Vision Pro, whatever, it still isn't released yet. We still didn't see how their 3D video looks, but this is like somewhat what it might look like, where you have a headset that and the video that was filmed on a phone, and from a headset you can see how it looks in 3D, like a volumetric video. And there's again like a video about the paper that I initially said was interesting. So basic introduction to video compression. I actually go through the post that I linked to here because it's a well done post about video compression. The core idea is you have lots and lots of HD videos on your laptop. For example, I have some movies downloaded and they're like 1 to 2 hours of video. And if they're in HD, we won't compress them, so we would store every pixel explicitly, like the 3 floating point numbers per pixel. Then it would come around to storing 360 megabytes per second. And so for a 3-second video, that's also already 1 gigabyte. And for a 2-hour video, I can compute this, but it's probably a terabyte or something. We wouldn't want to have a terabyte per video. So we have various video compression tactics, which, like, the basic ideas behind them are pretty simple, but nice to describe very easily. So, yeah, there's like a simple example where you can get from this first video to the second video, first PNG, just an image, to the second PNG with already 14x increase in size, while you barely see any change in the image. But that's for one frame. And there's ideas behind this, so this is a little bit math. I won't get too much into it. So you can do Fourier transform of the initial image. Fourier transform means that you can decompose a function into like lower frequency and higher frequency components. This can also be done for a 2D image. So I won't get into detail how this works. Point is, each of these, this image like implicitly represents this image, and we can modify this somehow, but still get this image. So, for example, all of these pixels in this image are like coefficient of a particular frequency component, and we can remove ones that are farther to the side, like that are higher frequency components, and still get basically the same image with just very slight changes. So we can like decrease our image 50 times while preserving most of the details, most of the structure.
So JPEG is working in a similar way?
Yeah, JPEG is working in a very similar way. So it does, I don't know, either Fourier transform or like discrete Fourier transform or like a discrete cosine transform, something like that. But it does not on the whole image. It splits the image into 16 by 16 blocks or something like that, and it does the discrete transform on there. Yeah, but this is for one image. For multiple images, what we can actually do. So we, when we encode a video, we just encode the first frame, and then for each of the next frames, so what I show here is that we have an image. I hope it's clear from this visual. So we have some kind of image, or 2 frames. We first somehow encode this frame, and we have the next frame, which is almost the same as the previous one, but with some slight changes, with some warping. So the mouth is open, whatever, the head is rotated a little bit. And so like there's a smart algorithm in this standard called ABC H.264 that computes like for each small block of the image how much it moved from one frame to another. And so instead of encoding this whole image, we can actually encode just the change that happened to the first frame. So we just store these vectors of like how each block moved, and then there's still an error where when we apply this warping on the first frame, and so we encode this error. But this error is much simpler, and it's much more efficient to encode this delta between our like warping and the true second frame. It's much more efficient to encode this than the whole second frame. That's actually like a very simple, another example I'd like to show. There's like a whole GitHub on video compression tactics, and there was an example that I really liked, but I can barely see it. So this is like 4 frames where the background is all the same. What moves is just the sphere. And so we can encode like the vector basically from which coordinate to which coordinate the sphere moved. This vector is stored in our like compressed format, and instead of storing the second frame explicitly, like actually in the file, we store the first frame and then reconstruct the second frame using this offset. But so this particular example shows that after applying this offset, there is still some kind of error, and this error is what we encode with like Fourier decomposition or discrete cosine transform. And this is like a quick trick that lets us use a lot less memory for this one frame. Yeah, this is another example. So like in this movie, we have the background that is basically fixed in place. So the motion vectors are basically points.
So all the squares is just the pictures without any interpolations, just the pictures.
I'm not sure.
According to previous slide, it's just a sphere that translated a little bit at the right.
Yeah. So from first frame to second frame, only the sphere changed. So we basically copy the background and the sphere we need to move. And so this is another example, like a cartoon where the character is moving, so there's like lots of motion vectors for the parts of the body of the character, and the background stays in place. It's basically copied from frame to frame. So this is the main idea for how to compress a video, like use a lot less memory. And there's like just a slight hint that there's a more widely used standard called H.264, which splits the image into regular blocks. And there's like a newer standard that does like smarter adaptive fitting of these squares. But this is not very relevant, just an interesting idea.
Some interesting comment regarding this technology of video compression. So when you like watch, for example, lectures, so this compression works really good because only moves like your mouth and maybe your face. And this kind of videos, they compress really good. But for example, if it's like an action movie, this compression works not good because it's lots of different scenes and lots of motions there. That's why this compression works differently on different kind of video in general.
Yeah, you can maybe sometimes observe that you watch like videos of fireworks, and the moment the fireworks start banging, the video suddenly drops quality because the compression doesn't work well with like lots of changes to the image. And if you have video of just pure white noise every frame, that it just doesn't compress at all. So yeah, the best kind of videos is where like this whole background in this video, for example, is just stable, doesn't move, and only I move, or the slides. Okay, so there's also like an ideal LZ4 compression. I'll try to explain quickly with the whiteboard. So this gives a little bit of hint of how it works. So for example, there's a whole. You can see this. For example, if there's a string like A, B, C, D, E, A, B, then in the file what we can do is store A, B, C, D, E, and then say like just copy these first two here. So instead of like explicitly saying this new substring, or maybe it's A, B, C, D, E, A, B, C, D, E. Instead of actually printing all of these 5, we can copy these substrings across the file.
So it's a classical compression.
Yeah, like LZ4 is classical compression. Yeah, just very widely used, and is also very fast to like very parallelizable. Also, one genius thing that I think is genius. So, for example, you have a string of just A, and there's 64 of them, for example. You wouldn't be able to properly do this with just the setting, right? You need to print the first A, then copy this first A, then copy these first two A's. You would need like somewhat like logarithm of 64 operations to copy all these A's. But there's a genius idea, so you can just encode one A and then say, even though you have only one A, copy first 63 characters to this position. So you don't have 63 characters yet, but when you start copying, so what is the first character on this position in this segment? It's A. What is the second character in this segment? It's A. And so on and so on. So you don't even have these 63 characters yet, but you can still copy this segment, which means that you can repeat A for 64 times, which is, I think, genius. Interesting. So this is very trivial, like very widely used, and is going to be used in some places in the ideas that I present. Okay, so prerequisites or juicy examples next. Woo! Woohoo! So also I like watching GDC game dev conferences lectures. They are very informative of like what technical tricks are employed in game development. And this particular one is my favorite because the Spider-Man game is very technically advanced and interesting, and this particular lecture gives very good insight into what tricks they used. So, and one of the things they mentioned in this presentation is that, so I'll just play this and maybe repeat some parts.
But on Marvel's Spider-Man, we used facial capture for almost all of our cutscene performances. The thing where you've got the camera and the dots on the actor's face and recording acting. The bodies and some of the head are skeletal animation, like the jaw and the eyelids and stuff like that. But the really fine detail, like the movement of the muscles and the creases and the wrinkles in the skin, it's very hard to do that just with skeletal animation. So for that, we decided to use morphs, and to get it right, we needed between 600 and 800 morphs per character, which is a lot of morphs.
This is like a small introduction into that they used very detailed like facial expressions and motion for cutscenes, where the character is actually expressing some emotions, and we need very detailed motions on the face. And so they used the system where they asked a separate company to scan faces of actors. And then they have these
there's the joints going, there's the blend shapes for the really fine stuff.
Blend shapes where you can configure different expressions. But that's not the point. The point is that they said that it's too expensive to compute all these blendings in runtime, so they have all these expressions, and each separate expression is like a weighted average of all these predefined expressions. But it's too expensive, like too slow to compute this at runtime when this cutscene is playing, so they just need to pre-compute this offline, all of these blend shapes, and then stream all of the facial movements, all the separate vertex movements in runtime.
So just when we say compute, we have like a 3D mesh of the face,
yes,
and you have this parametric model,
yes,
which can distort it somehow, and like computing this is hard.
Yeah, so this, computing all these informations to the mesh is hard.
Like this one particularly, I mean, like with these movements of these signals, it's highly vivid, but the mesh of the face. So I think in every like a frame you need to recalculate every particular triangle. This should be, I think, multiple part there. That's why they recompute. I expect something like this, but I'm not sure.
So they say that they just bake it all the animation in
Yes.
one big texture.
Yes.
And just read it.
No, not texture, just format that I'll explain. So yeah, usually animation is like you have a skeleton of your body, which is your body maybe in this game consists of like tens or hundreds of vertices, but a skeleton is like tens, just 100 bones, I guess, that lie in your body, and they move these bones, and with these bones move all of the vertices of your body. But this animation is like how the movements of bones correspond to moves of vertices. It's like a computation that is hard to run at one time. So this is something they bake offline, so they compute these per vertex movements offline per frame, and then stream all of these vertex changes during the cutscene.
Together you can get performances. Addition is you can stream these faces.
So yeah, each of the faces is very high quality. It's 18,000 verts per face.
The
And they
face
can
that
compute
gives
that.
3 vectors per vert. Position the normal for the lighting. 3 floats per vector at 30 frames a second is 20 megabytes.
80,000. As Sasha said, like usually in games we explicitly store the normal and tangent per each vertex, even though they can be just computed analytically. But usually in games you store that explicitly, like somewhere in the file. So yeah, the initial idea is that you can just stream all of the data in real time, but that way you need to load 20 megabytes per second, which is hard when you have all of the. You know, it's also hard for me to understand like what is too much for real time, what is not too much. But this was too much. So per face, when you have multiple faces at the scene, when you have like lots of backgrounds and other effects, this is too much to load per second. So we can run different optimizations.
Turns out, skin does not move more than about a centimeter from your face while you're still alive. So we can get away with using fixed point notation for them.
So first is quantization. Quantization is like a general word for compression, or in machine learning you can also hear quantization because you need efficient models which are faster and to run. And usually there you decrease the floating points, which are usually 32 bits per point per number. You can use fewer bits, and so here they say that just each of the numbers can be stored with 10 bits, and so each vector is now 30 bits. So it's 3 times decrease, approximately, which already got us to from 20 megabytes per second to 6 megabytes per
bits for
second.
every component, 30 bits per vector. Also, the normal and the tangent, right? Like, what if I told you there was something called a cross product that you could use to work out the normals just from the positions? Why? Let's step back. Like, why do we store normals and tangents in meshes and textures at all? It's to save on runtimes, because calculating all that stuff would be redundant. Except in this case, the bandwidth was really the scarce thing, and we actually had a lot of CPU time left over because there's not a lot of sim going on during a cutscene. You're not swinging the city, nobody's AIing at you. So we ended up just as a compression tactic, streaming just the positions and doing the normals and tangents.
This is what Sasha mentioned. Usually in game dev we store normals and tangents per vertex explicitly. We don't need to do that. We can just compute these. That's what we get. But that's not all.
Runtime. Yes. You're 2 megabytes a second with careful arrangement. LZ gets us down to.
Yes, LZ, careful arrangement. So they, in the next slide, they say that they arrange these all these numbers in a way that is very efficiently LZ compressed, which gets them from even more efficiently from 2 megabytes to 0.5 megabytes per face.
Per face, with joint positions for all the.
So yeah, they just do this. They need to stream all various positions at runtime. They just do it like this. Just all of the X positions for this frame first, and all of the Y positions, all of the Z positions of the vertices. And
characters, followed by all the vert positions for all the characters that vert stream. We do the structure of arrays thing, so that's like all the X components for everyone, and all the Y components for every vector, and then all the Z components, because it compresses better that way. Also, we delta compress these things, so for frame 2, every vert position, it's not the absolute position, it is the difference from its position in frame 1, because most verts actually don't move from frame to frame, which means we have these long runs of zeros, which LZ4 eats up. Obviously this makes scrubbing really annoying, but the player doesn't scrub.
okay, so as I said, not as I said. I mean, they don't need to stream all of the vertex positions explicitly. They can just stream the movements, like the motion vectors of the vertices. And because they are usually very close to zero, all these movements, they are very well compressed with LZ4, as he said, which is going down to almost the same for all characters, loading times. Great, like lots of good ideas for streaming vertices in runtime, and there's also some fun.
This is for things to go wrong. Joints are verts, and verts are joints. Also, if you have like a black spot on a character's face, what's going on there, right? Is it missing? Is it missing from the mesh? Is it the wrong position? Is the lighting wrong? I'm not gonna talk over this. Yeah, so somewhat belatedly we realized we needed a tool where we could render just like one streamed face in an app of its own and then point. Why did I do this?
Okay, so yeah, this is probably my favorite like technical presentation talk ever. So go watch this. This is really good. Yeah, so this is it for game dev ideas that I know about. Yeah, also, quick mention that I already said that they use like the blending for faces. Usually you have skeletal animation for all animations, but here because faces are so like, detailed and so complex, it's hard to express facial animation through bone movements. So instead they have like these predefined expressions, and then they have like coefficients to blend between these expressions. Which is called morphs. So like they use morphs for animation. This is what morphs is. Okay, so this is it for game dev ideas. Now for research, I found like a really good survey on mesh compression ideas that is 2 years old, so it's pretty recent. There's lots of stuff. This is like a graph of all of the approaches there are for mesh compression, but I don't want to go through all of these, of course. I picked out the most interesting ones. So I'm going to probably use the whiteboard a lot. So as I said in the prerequisite slides, a mesh is a combination of vertices plus faces. Vertices is the positions of all the points. Faces are all those triangles. And most often, like most of these methods, are compressing them separately because these are two different types of data. Vertices are floating point data, and faces are integers, which are indices to the vertices. So, like one of the quick ideas. Again, I want to show you the frog. This is not a frog. Frog is a quick example of how the mesh geometry usually looks. So as you can see, it's a pretty regular grid. So most of the vertices have 6 neighbors. So each vertex has a degree or valence, sometimes called, which is the number of vertices it's connected to. So most of the vertices have 6 neighbors. And the grid is pretty regular most of the time. So most of the triangles have the same area. So most of the meshes are like this. They're pretty nice. This can be used in compression algorithms. So one of the very simple ideas is we can notice that there's lots of structures like this in the mesh where we have just triangle strips. We can have one triangle and then the next one is connected to the previous one, the next one is connected to the previous one. And so instead of storing like each face like 0, 1, 2, 1, 2, 3, so this triangle strip, for example, would be sort of like 0, 1, 2, 1, 2, 3, 2, 3, 4, and so on. We'll store each.
You just flip the normal.
What?
You just flip the normal of the last
Oh,
triangle.
whatever. It's yeah, the details another time. So yeah, we could store it like that. This is the way it's stored in the object form, the typical format. But because of the other strips of triangles, one after another, we can say that like the first face is 0, 1, 2, and then the next one is connected to the previous one. We can just say that the index of that triangle, the new index, is 3, and it should be connected to these two. We can automatically infer that. Then 4, it should be connected to the previous two, so to this one and to this one. Then 5, connected to this one and this one. So we don't need to say 0, 1, 2, 1, 2, 3, 2, 3, 4. We can say 0, 1, 2, and then the next triangle is just 3, which is connected to the previous two vertices, and so on. So we already use for each new triangle 1 number instead of 3 numbers, which is like 3x compression already.
And
Nice.
that's balance encoding, right?
No, sorry. So we can balance encoding is a different thing. I'll try to explain it later. This is we use the triangle strips. So we just write all these the sequence of indices as a triangle strip. We can also say basically do the same with this, where we have this is the structure called fans, where it's a single vertex and just connected with this like fan, or how do they call this, to lots of neighboring vertices. But we can just say that like there's 0 and what, 4 other vertices that it's connected to. So instead of saying that like each of these 4 triangles, we just say 4, and then it's automatically connected to the next 4. 1, 2, and 2 is connected to 2, 3, and 2 is connected to 3, and so on. And we can decompose our mesh into these structures and store these structures in a file, and so like compress it a lot. So this is using triangle strips and fans, which are these structures. For valence encoding, so valence encoding is interesting. There's a paper. So the survey says that valence encoding is still like considered one of the most efficient and pretty widely used tactics for mesh compression. I don't know where instead of aside from game dev mesh compression is used. Actually, this paper isn't very helpful. There is not lots of visuals. What I want to show. Yeah, so this page has most of the ideas. So the idea is, sorry, it's going to be easier if I just show on this mesh. Valence encoding. So valence, as I said, is pretty much the same as degree. So valence is the number of neighbors of each vertex. So for example, we have one triangle, and we start like working, compressing from that triangle. This triangle probably has 4 more neighbors. So we take first vertex here. It has 4 more neighbors. And for each of these neighbors, we'll order them. And in the file, we write the valence / degree of each of these vertices. So first in the file, we write 6, because this vertex has 6 neighbors. This vertex has 6 neighbors, this vertex has 6 neighbors, and so on. Then we go to the next vertex in this triangle. It also has 4 neighbors. Each of them has 6 neighbors, 6 neighbors, 6 neighbors. Then we go to the next one here. And suppose this one now has, like, 4 neighbors for some reason. We just go in a particular order, in a predetermined order, and write the valences of each of these vertices. 5, 6, 6. Now that we have all of these neighbors, we can order them in a particular order, that is, we can know them both in encoding time and the decompression time. And we do the same for them. So just write the balances of all these. But because we already know the number of neighbors during decompression, also we know how many neighbors does this vertex have, right? So this is how we encode it. We just write in a particular order the balances of each of these vertices. But during decompression, we start from one triangle. Then because we just start from this and say that, okay, we have all of these vertices in order, but because we know the valence of this vertex, the valence of this vertex, we know how many vertices are we need to connect this one to. And then we jump to the next one after the valence of this one is empty. So this is relatively clear. I see 2 nods. Should I somehow rephrase this or repeat this?
So it's just an order how
yeah.
how it's stored, but there are actual data with coordinates. Not only the tree, this kind of tree structure.
Oh yes, so sorry, I forgot to mention. Right now I'm discussing the ways to compress the faces. The ways to compress the vertices are in the next slide. So yeah, this one is cool because we only need to store the valence or degrees of each vertex, and then we can automatically traverse this mesh using just the valences because we know when to end traversing each vertex because we know its valence. We also this tactic also needs to be able to take a mesh and split it into 2 because this way we can only encode a mesh like this, which is just it won't be able to encode a sphere, a whole sphere, because this one only creates new vertices and doesn't stitch a single mesh to itself, right? So we need to be able to take a mesh, split it, and then encode those split parts. But the core idea is this, and why it's so efficient and so cool is because, again, as we said, most of the vertices have 6 degrees, which means that LZ4 eats this up very well. So we store only valences, and these large rows of mostly 6 are very, very well compressed with LZ compression. Yeah. This is valence compression, and a simpler idea is that suppose we already have the vertices. Who knows what Delaunay triangulation is? So basically, it's for people who are not familiar. I can just Google this quickly. Delaunay triangulation. It's basically like a smart method for when we have lots of points. So initially, we just have points scattered on in 2D, and we have a method to make a nice regular triangulation of these points. Right? It's a pretty tough algorithm. I tried to implement it at some point. I didn't manage to do so. It's tough to implement. So yeah, this is a better example. We have just a set of given points, and they're Delaunay triangulated in a pretty nice structure. And so this same algorithm is similarly implemented for 3D. And so when we have vertices from somewhere, we can just get these vertices and then apply the Delaunay triangulation on these vertices and get like a surface that is probably very similar to what our actual mesh is. And then we can just encode the differences between this Delaunay triangulation and the actual faces, and which is probably much more efficient than like encoding the faces themselves. Okay, and now for the vertex compression. So again, like the core ideas from the research is that we can do the same quantization as in the game dev scenario, where we just initially, most of the time, we use 32 bits for each floating point number. We can instead like use 16 bits or 8 bits or whatever. There's lots of ways to decrease the number of bits for each number, and mostly we won't lose any kind of accuracy on the vertices. So this is like a 2x, 4x decrease in file size. We can also do vector quantization. So vector quantization is not exactly like quantization. So this is an example for a 2D case where we have lots of 3 points, and we group them in some way. So this is like nearest neighbor clustering, so for each point we encode it with the index of the nearest cluster, and we encode this offset. So I will draw on the wall. We have lots of points. They're grouped like this, like this, like this. So for example, this particular group has this center, or the centroid of this group, right? And so to encode this particular vertex, we first store an index of this particular centroid, and then we encode this like vector from the centroid to this vector. So the number of clusters is the number of centroids we need to store. So all these centroids, like this first centroid, there's a centroid here, centroid here, centroid here. We store the positions of these centroids explicitly, but then for each of the vertices in each group, we store the vector from the centroid to this vertex. And so these vertices are usually like they're like from 0 to 1. We can use a lot fewer bits for them than like in the whole absolute space. So this is another way. We group them and then represent each vertex from each group. Vector quantization. Yeah, so the delta prediction is very similar to what we saw in again in game dev, where we store the vertices of each next frame as a delta. So for example, we have a mesh. It's lots and lots and lots of vertices. For example, we have. I'll just show the frog again. And so we have this vertex, this vertex. We can order them in a way that they go in a straight line. And so, for example, they're ordered in the file like this. This vertex, this vertex, this vertex, and so on. They are one after another. And so, for example, I have this vertex, and instead of encoding this absolute position, I can encode this delta, for example. And so this vector is encoded, and then I encode this vector, and then I encode this vector, and again, because we probably apply LZ for compression afterwards, these delta vectors are all very similar, and so they're probably just going to be duplicated and compressed very well if we order these vertices after one another very well. There's also second order compression, where again we have these vertices one after another. For example, assume we have this first vertex V1, first vertex v2, there's a delta, and then we store the second order delta. So we store the delta to apply to this one. Assume our vertices are like this. So this is our new vector. And we use this vector to get our next vertex. So the same as before, but now we encode like the second order derivative. And I guess it also is used somewhere. And yeah, it's like a weird idea, but for some reason it's very widely used. Where we already have a structure of our mesh, the faces, and instead of storing like the delta from between two vertices, we have like a triangle, and then we compose a parallelogram from this triangle. Like we duplicate this triangle and flip it like this. And so new vertex for this mesh is somewhere near this point. And so we just encode this delta between this prediction of the extend parallelogram and this true point. And we can either like extend one parallelogram and store this delta, or we can extend two parallelograms, average them, and store the delta between the average and the true point. So there's lots of tricks like this, but for some reason this is very widely used. Okay, so this is it for mesh compression research. Now we go to the even more fun stuff. Okay, so who here knows what Gaussian splatting is? Okay, I see more hands. So it's a new method that came out this summer for like 3D reconstruction. So we saw an example previously for how to reconstruct objects. This is like a very simple one to show. So we have a teddy bear, we film it from different viewpoints, and then what we do is we represent it with these like ellipsoids, spheres, whatever. They compose this teddy bear, and we can see that like when these ellipsoids grow, they slowly start to resemble the teddy bear more. But this example uses like very few, probably 40 of these ellipsoids, where in truth for like very large scenes in which we want lots of details for, we can use like hundreds of thousands of these ellipsoids. For example, this is like probably 300,000 ellipsoids, same as in the teddy bear, but for this like very complex scene. They have an example that shows. Yeah, so this is like another scene that is rendered with a 3D Gaussian splatting, and they show that.
Scale down their extent.
So they quickly scaled down each ellipsoid, and you can see that how each of the objects is represented with ellipsoids, like this. If we scale them back, so make them larger again, we'll see the initial height again. So again, each of these like very thin sticks is very thin ellipsoids, which stretch along the sticks. So again, this came out this summer. And it's very, very popular because compared to NeRFs, they're faster to train and render, they're very flexible, and stuff like that. And so for context also, even for people who very well know about Gaussians, this is a paper that the Gaussian splatting paper cited, which I think is very good for context because it's a paper from 3 years ago, it's, 4 years ago, whatever, which does the same but with solid spheres. So Gaussian splatting is semi-transparent spheres like Gaussians, whereas this paper, it's efficient sphere-based rendering. So, for example, these faces are rendered like this, and it's composed of spheres, like actual solid spheres, which are colored in a particular way. Which is interesting. It works.
Some questions. So, without, for example, NeRFs that was like discovered in 2020s, remember? Gaussian splatting is could it like be discovered because they look like pretty similar, but in the NeRF you just find out a particular pixel and the color of it, and right there you just try to find out this ellipsoid there.
Mm-hmm.
So it looks like that without the NeRFs, these methods couldn't be developed.
Yeah, I think it's very motivated by NeRFs. So usually it's told as like Gaussian splatting separately from NeRFs, that it's a method for rasterization instead of volume rendering, but I actually gave a paper reading club on Gaussian Splatting too, and there's a very clear parallel between NeRFs and Gaussian Splatting, where you can like derive the same formula as a NeRF for Gaussian Splatting, and then say that like, oh, we can do actually rasterization instead of volume rendering, even though we started with volume rendering. So I think there's some fun math, but yeah, I think without NeRFs, maybe Gaussian Splatting wouldn't be so well developed right now. But yeah, also for context, I think this is nice. So there's was a method that does very similar thing, but not with Gaussians, with spheres.
I have a question. How long do you estimate to talk? Just
so
if you maybe need to make.
I have 4 more slides, so 5 more slides.
Okay,
I think
great.
So yeah, there's a couple of posts. Like there's one guy who worked in Unity for 20 years or something, and he does great posts on different topics and books. But he got onto Gaussian splats, and he made 2 great posts about how to compress them. So these like classic scenes, I'll just go through this post, it's very well made. These classic scenes for Gaussian splatting all weight like from 1 to 2 gigabytes. Okay, this truck scene weighs 600 megabytes. This is a lot, even though we still want detailed scenes, but having like 1.5 gigabytes for each scene is not nice. So he says he can make it 19 times smaller, but we lose lots of details. There's some artifacts occurring, so there's a trade-off between quality and storage size. So main ideas. First, we can. This is like the order if we just plot the index of each splat. This is how the order. They're very chaotic. This is basically the order of Gaussian splats. We can make it so we order them in such a way that, like, in the file, nearby splats also are near in the 3D space. So we use 3D ordering for this. This is a way to sort 3D objects using their positions. So again, like the color here is just their index that is mapped to some color. So we see nearby splats in terms of indices stay near in the 3D space. Who knows what 3D Morton ordering is? So it's actually a pretty simple idea. Maybe you saw this somewhere. It's a Z curve, which is like a way to fill a space with a one-dimensional curve in such a way that nearby points in the 2D space will also be nearby on the curve. But also this can be applied for 3D space. So this is the thing that they do here. They use this like transformation from 2D or 3D to 1D, and this way they sort the Gaussians. So what they can do then is, so what this guy does, he groups them into chunks. So the trivial idea that he has is that he can sort all the data for each of the splats, which is the position of the splat, the color of the splat, and then there's like the view-dependent components called spherical harmonics. I don't want to get into the details of what spherical harmonics is. It's just like a few coefficients that let the color be different from different sides. And so all of this data can actually be stored in textures. Before we stored it like in a file where all of the all these components were just one by one stored in the file, but we can store them in a texture, just in a 2D way. And we have lots of good compression algorithms for 2D textures. So we can just store these 256 chunks like these rows and compress these rows and get, so this is just examples, and get compression that compresses about 12 times the file sizes, but we get like lots of artifacts and bad stuff. What we can do we can do different is that we store all of these segments in these rows, but these segments are actually, like, compression algorithms work better when there are similar blocks. So what he does is put these chunks into blocks, like this. So this is now like data for nearby splats stored in blocks. So each of these blocks is 16 by 16 pixels. And this is a lot better compressed with image compression, like texture compression algorithms. And what we get from this is, still 12 times decrease in file size, but we get a much better metric. in terms of like quality of reconstruction after compression or and decompression. And there is of course quantization that we can apply, so each of the numbers can be represented with a much smaller number of bits. And so this guy, what he gets is he can do basically like 0.8 compression without any loss of details, 3 times compression with a very good metric, and then like 12 times compression with a pretty good metric. So PSNR is hard to interpret, but 34 is good enough. 47 is very, very good. And very low looks like this, for example. So this truck, of course, has many, many issues, but we can still see that it's truck. So yeah, we can get like 19 times decrease with these detail losses, but we can also get 5 times decrease with pretty much the same scene. Now there was an expose that expanded this one. That makes a few other ideas work. This one applies vector quantization. So remember how we grouped 3D points on the mesh and then represented them with the centroid of that group. We can do the same but with colors. So a color is also like a 3-dimensional point. We can vector quantize the colors, all the colors in the scene. And this is actually it's an old method of image compression called like paletting or something, where we just take the RGB colors of our image and then we store the palette and then store the index to the color in the palette. We can do the same with the RGB colors of the splats and the spherical harmonic coordinates and colors. This like paletting, which was again very widely used for image compression, which is probably used in some image compression standards, gets us even smaller file sizes. Like for example, on the same preset using the same tactics, but now with this idea of paletting, gets us a smaller file size but a higher metric of quality. Okay, so a few ideas that are pretty nice, and for Gaussian Splatting, I think this is very relevant.
I have some more question. What is like your gut feeling, maybe in multiple years? What kind of size you could achieve with the cuts of splitting these 3D files? Because it's have like for me a direct linkage between usability and the amount of weight which we used on hard drive there.
So you mean like my prediction of how much the file size will weigh in?
Yeah.
Sorry, I got one second. So my prediction is actually that I'd like to focus on like my personal interest in why I think this should be improved is like coarse-to-fine file sizes where we load these Gaussian splats, but not the whole file. We first load the very coarse representation, like this very, very low preset. We see this, and then procedurally we load the higher quality. And so the higher quality I think will still be like, I don't know, tens of megabytes, but the point is that we need like a fast first view on the Gaussian splatting scene, and so we'll have like a very low preset first that we see, and then it's slowly going to be loading more. So just like in games, usually you have like you load the scene. First it's like the low quality textures, and then like slowly you get higher quality textures, and you get the higher quality scene.
You see like the potential in the video game. I'm just thinking more about the potential in mobile phones and usability for the real customers and who will use it on the mobile phone. That's why they have not so big storage there. That's why if they like use the spatial photogrammetry, yeah, it will be great if it's like way less.
Oh, so you're asking whether this would be used instead because it's like weight less?
I'm thinking where it could be, when it could be used in the future.
So
because right now I don't see a lot of technologies there on the market that's really used right now.
So for example, VR immersive video. So I think there's going to be in the future a good market for like 3D movies. So this VR immersive thing that I showed, it's like pretty sweetheart movies. They're nice to watch, and right now they're using, as Pasha said, probably like a different representation, not NeRFs, not Gaussian Splatting, but some other representation. But I think Gaussian Splatting could be very well used there. for games, I don't think like games will actually have Gaussian splatting in them, but this is a good intermediate representation. So you have like these photogrammetry algorithms that are used in some games. So they instead of making the 3D assets from scratch, they scan things in some kind of software, then they convert it to a mesh and use that in the game. So instead of using photogrammetry algorithms, they use either NeRFs or 3D Gaussian splatting as an intermediate representation, and then convert this to meshes.
I think bottleneck there that you need to convert the Gaussian splatting to the mesh of the game engine.
Yeah.
This is a big point.
This, when I gave the talk on Gaussian splatting, there weren't very good ways to convert them to meshes, but right now I saw some papers that do it very well. So there's Gaussian Dreamer, I think. This paper. No, not this one. Or it is this one. So basically, there was like this one paper that does a text to 3D synthesis. Basically, you give a text description and then it generates a 3D object. This one works with Gaussian splatting, and then this particular paper implemented a pretty good like transformation from the 3D Gaussian splatting to meshes. Maybe it's not this one. Whatever. So there is already a pretty good algorithm for converting Gaussian splatting to meshes. And there's a Rhode Island slide for some reason. Okay.
Can you later share that paper in the chat?
Which one? The Gaussian splatting?
Converting Gaussian splatting to
Oh,
mesh.
sure. Yeah, remind me. I'll share it. Yeah, I'll find it.
3D Nights, that chat.
The paper reading club chat.
I'll also share it to the 391, but yeah, mostly I'll share all the presentation and all the links to the paper reading club.
Paper reading club.
It's there's a chat for hackerspace this place, and there's a topic in the chat, paper reading club.
Okay.
Now NeRFs. So it's actually like kind of the wrong order because first came NeRFs like 2 years ago. A paper like the original NeRF paper. It was like very raw. There were a few ideas, but it works. It started like a whole 3D reconstruction boom. And then after that, this summer came 3D Gaussian splatting. So the idea of NeRF is that, so it's the same. You have 2D images of something. In this case, like a very popular example there is this Lego truck. They have 2D images, and then they somehow get this 3D truck. But what is this 3D truck? So actually what it is this function that gets a position and the viewing direction. But first we can just think about the position. So this function that gets the position of a point in space and then gives us the RGB of that point and the density at that point. So the sigma, this like mathematical sigma, it's a density of the point. So for example, if I take a point at this like siren on top of the truck, it will have a color red. So this RGB will be like 100, the red color, and the density will be 1, which basically means solid, because this siren is solid material. And if I take a point somewhere outside in the air, so this 3D point, it'll have a density of 0 because it's not dense, it's not solid, it's a point through which the light ray will perfectly pass through. And the RGB like an arbitrary RGB because when the density is 0, it doesn't matter which RGB is at that point. And so if we can basically say that like we understand what function there needs to be for this truck, right? If we take any point, we can say that there should be yellow color, 1 density, black color, 1 density, like density 0, color doesn't matter for each point, right? And so if we have all of these images, we can actually get this function by training a neural network that represents this function. This is the idea. The core algorithmic thing that this paper developed is the way to render having this function. So, for example, we have this function that gets us an RGB and sigma for each point. And how do we produce the image when we have this function? So there's this volume rendering approach that samples lots of points, sums up in a smart way, sums up the colors and the densities, and gets the color for that pixel. And so we can do this for each pixel and get the image from that point of view. So we use this both for rendering and training when we already have the function. Okay, we have images, we can get this function. We get it by training a neural network. And the zip nerf that I said here is actually, it's not just a neural network. There's lots of ideas for simplifying the job for this function / neural network. And again, like
Hi, I'm John Barron from Google Research, and this.
It gets results like this. So the initial paper managed to only reconstruct like a single truck, barely, and this paper managed, like from half a year ago, manages to reconstruct this whole scene, a very large scene, very well. Yeah, comparison against other models, whatever. But yeah, so this state-of-the-art approach is renders at 5 FPS on a V100. So again, a V100 is like a very powerful GPU specifically for training neural networks. So 5 FPS there isn't very friendly to mobile devices. Whereas Gaussian Splatting renders at 100 FPS with the same hardware. And there's like a 300 megabyte model to represent the scene.
Questions.
Yeah.
This algorithm, it called NeRF.
Zip nerf, yeah.
It contains some photos from several positions. But
Yes. So the input to the algorithm is the photos of the truck and the accurate camera positions of the truck.
And what is how this algorithm reconstruct this object?
So how do we get the function? So I said that we have all the images, and then we train the neural network such that the renders from this neural network will match the input images. So at first we have like a neural network that produces a very random image. So we have these two trucks images. Whatever.
Well, wait, I think the question was actually how they reconstruct the mesh, and they don't. There is no mesh.
So,
But you could create
a lot of years ago, I have deployed on this some nearest things, and I reconstruct this by algorithms on.
Model adjustment.
I don't know how to say in English.
It's a photogrammetry.
Да, эти биологическими вот этими генетическими алгоритмами восстанавливается вот этот вот как бы объект. И он, грубо говоря, была функция, которая сравнивала как бы, то есть она, грубо говоря, придумывала объект, смотрела, могла обратно перейти на английский. When some object we reconstruct, then make a lot of photos from different views and
compare.
And yes, and compare.
So we mutate, we
basic,
merge objects.
Yes, and after that we change by this genetic algorithms first some of this object and find the real object that should be nearest with this. And it was very very heavy and
slow.
Slow on that computers in that time, but it's very calculative.
Inefficient.
Very bad.
Computationally bad.
Very big calculations for this, and I want to understand: is this the same algorithm?
How this works? So that genetic algorithms work like this. We have some kind of reward or loss function. We need to minimize it so the actors in the genetic algorithm that get a higher reward survive. The slower reward they die out, and then we mutate the better ones and kill off the worst ones. So here we have a loss function. We have this sum theory representation. We get a render from this theory representation, and the mean squared error loss between the render from this and this true image is like our loss, which we want to minimize. Or this is like the error or the inverse of the reward, right? So we want to, as you said, like you have an object, you get a render from it, and then you compare the true render with the render of your object, right?
So it might also be the case that we have the recording of your talk on that, exactly? Do we?
What?
Do we have a recording of your talk?
I have a recording of the NeRF talk, it's 2 hours long. I can quickly explain the idea.
Okay, just saying that we have a recording of the full talk.
I have a recording of the full talk.
In Russian.
Yeah. Basically, the idea is that you have this error in your algorithm, but we have the same error, but it's differentiable. We can get gradients from it, and so we can use gradient descent. So instead of a genetic algorithm, we use gradient descent to minimize that difference.
Yeah. So like the key difference is that we have we can do smooth optimization instead of like discrete optimization, and it works better.
Just maybe more robust in general.
Yeah.
So you because this is like you could think about like a black box in the end, and it doesn't matter a lot. I think this is one thing that you a bit miss when you explain it. That actually we need to train every time for every particular.
Oh yeah, this
scene.
is like a concept that is sometimes miss. So usually we train neural networks as classifiers. For example, we have a large data set, we train this neural network on lots of cats and dogs, and then in any new scenario we can differentiate cats and dogs. So we have this neural network, we just use it, a pre-trained neural network. But here, we train a neural network for each scene, for this new scene that is like many 2D images. We start a neural network from scratch and train a neural network to represent this function from like positions to densities.
Architecture of neural network is the same. We are retraining the weights for each.
Yeah, well, the architecture is the same. We just retrain for every new scene. Yeah, so yeah, if this is clear, I hope I can refer you to my other lecture on NeRFs, which is very comprehensive.
Probably the difference between this not evolution, but kinetic algorithm is that with this gradient descent, you could, we have a lot of good optimization techniques there with Adam and so on. You could find like the best spot, maybe even better with the genetic algorithm. This would be the key difference there.
Generally, the difference between
Yeah,
zero order optimization methods and
Whereas you are
first
talking about
order
the
optimization
optimization
methods.
of the weights. His genetic algorithm was recreating the object. It was not applied to optimize a neural network. That's why there is such a huge difference.
Yeah, of course, but I'm not sure if this genetic algorithm could be used like as a or so you train it once or you train it for the another scenes again.
No, actually.
This is the maybe will be interesting.
Yeah, I don't think
to
it's
check.
that much of a difference because your mesh is an approximation. In a way, your mesh of triangles is again kind of function that approximates the shape, and then you have neural network that again, basically a bunch of
Here we
numbers
are talking not
with
about
approximations.
This thing generates volumetric data, and there is the problem with all those how you explain that this rendering is so slow. The main problem is that NeRF initially didn't provide any optimization for occlusion. So to render it, we had to do a ray tracing front and then wait till we'll hit the first volumetric the first return from this function where the last parameter, which is not density, it is opacity. Where the opacity was, and this way we needed that okay, after this we don't need to extend this ray because we don't need returns of this function. This spot already occludes everything, and all further optimization are generating basically the frustum pulling the frustum so to speed up, to minimize the amount of data we need to retrieve from this function to render the image to film.
Well, that's true, but these are kind of
His
different
algorithm
levels.
is completely different. He's talking about he was using genetic algorithm to recreate the 3D mesh, and then they were rendering things. NeRF kind of takes over that. We don't need 3D data because we are operating basically with voxel data. But this, since this function, we can.
This is 3D data. Okay, there are two sides of this coin always. You have some representation of your scene, and then you have some method to render it. Again, with meshes, with NeRFs,
So
whatever.
maybe just a suggestion. Let's just finish the last two
Yeah.
slides and then like
Let's
get
postpone
another
and during the
more
break you
round,
can
yeah.
discuss this. Yeah. So I already went to this slide. So this is the paper that I initially wanted to make the whole introduction about. And we'll go through this briefly because most of the cool ideas were there on the previous slides. So this one, I'll just open the paper and show the cool ideas that I think are cool. So, la 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 la. So first off, the main difference between this approach and most of the NeRFs is that, as I said on this slide, we need some kind of function that returns from the coordinate, the RGB, and density. This approach, this particular approach, simplifies the job a lot by training a voxel grid of densities and features that we interpolate. So this uses actually like an algorithm called dvgo. 1 second. Dvgo. Yeah, it's an algorithm that stems from NeRF, which is still a NeRF, so it's predicting an RGB and density at each point. But instead of having just a neural network that predicts for each point the RGB and color, RGB and density, it has some large 3D grids, like 200 by 200 by 200 and larger, which contain densities and features that are then processed by a neural network. So this simplifies the job for a neural network. It's still a function, it's still a NeRF, so again, as in on the slide, we need just any kind of function. And this function is still, we just sample a cell at this 3D grid, and then pass that feature to the MLP of a neural network. So what they do for this approach for streaming video, first they just blatantly reconstruct every single frame separately as a static NeRF. They have a rig of like 50 cameras looking at the actor. They use these 50 images to reconstruct every frame separately. So there's like, I don't know, a few hundred NeRFs, static NeRFs. And then they need to stream this somehow efficiently. So now the ideas for how to stream this efficiently. First, well, the main idea that I think is pretty nice. So I explained that there's a thing called Z order or Morton order that orders like 3D data or 2D data in a way that like it's so consistently like points that are more close in the 2D space or 3D space are still close in the 1D space. And so this is used to where is it? Here. To convert from 3D space to 2D space. So how it's done? We have a function to convert like the Z order from 3D to 1D, and then we do from 2D to 1D. Now, why do we do this? We can now compose these two functions to get a conversion from 3D to 2D that preserves the distances between points. And so now all of these features and all these densities in the 3D space, we store it in a 2D image, right? And this 2D image is very well compressed with existing compression algorithms. So what we do is just take our 3D data and convert it to a format that is very well compressed with existing, very well engineered 2D compression algorithms. And so this is like the trivial approach, where we instead of making this 3D to 2D for the whole scene, we split both the 2D image into 16 by 16 blocks and the 3D scene into like 156 chunks. And so this 156 chunk is converted to this block in the image, and so all the video codecs and all the image encryption, or not encryption, compression processes images at 16 by 16 blocks mostly, and so we utilize that. So we also process the image, store this 3D data in the 2D image using 16 by 16 blocks. And because we use Morton ordering and not some arbitrary mapping, all these 16 by 16 mostly contain very similar data, so the RGB colors at the nearby points will be similar, the density at nearby points will be similar, so this block will also contain very similar data, so it's very well compressed. This is the first idea. We use Morton ordering to convert it to 2D space and then use existing 2D compression algorithms to compress this image. But, again, this is like an idea for a static frame. So, for example, if we had just one static scene, one static 3D volume, we'll use this to compress it with to the image. But yeah, but because we have like lots and lots of these 3D volumes, frames, grids, all of these are converted to this 2D texture, and these are streamed as a video, and this video is compressed with a video compression. And so again, because we use the same mapping every time, it's also very like not changing very much from frame to frame, because like some of the objects in the scene are static, so these this data won't be changing a lot. So the video compression will also work well because we use the same mapping, and so this block will change not very much from frame to frame, and so this will be very well compressed. But also, there's some ideas in this paper about how instead of having a 3D mapping from the whole 3D grid to the 2D image, we can use an occupancy map. So not the whole 3D volume is occupied, so as you can see, like there's a human, but lots of the 3D grid is actually like very free, so there's zero density, and we don't need to like store features in there. So they construct a 3D mapping specifically for this area where the human is located, and they do Morton ordering on these cells instead of like Morton ordering all of the cells in the 3D grid. And then they stream this as a video. This video is then decompressed on the mobile device. It's then using the same 3D to 2D mapping inverted to a 2D to 3D mapping and converted back to a 3D grid on device, and rendered on device using this 3D grid. And so I don't want to waste too much more time. There's also like lots of some tricks for, again, like efficient rendering on device, because this wouldn't get us fast rendering, 30 FPS. There's also a few ideas for how, when having this grid, we need to do efficient ray marching, and how do we call neural networks in a way that isn't very slow for a mobile device. But yeah, this may be for another time. Most of the cool ideas I think I mentioned. So again, core idea, just we have lots of 3D data, just to do a smart reordering it into 2D data and use existing compression algorithms of video to stream it very efficiently. At like what, 30 megabytes per second, I think they said. When usually like one static NeRF is like hundreds of megabytes. So again, very impressive. Yep, I think this is it. Any questions? Whatever. Yeah. No. Okay.
Yeah, so what happens now? I suggest we take like a 10-minute break to just come up, stretch our legs, do that. Maybe grab a drink upstairs, get some tea, use the toilet. And the next talk is going to be on privacy preserving statistics and machine learning. I will try to talk with you all more because this was covering a lot of ground, a lot of ideas. I will try to cover fewer ideas, but maybe in a little bit more depth. Yeah. Cool.
Should we pause the recording? Should we pause the recording, or should it go on?